Everything that we covered last time, do I have... Oh yeah, if you want to know more about this, I did leave some notes on here. So in Fogler, these energy balances are again taken from that same chapter 8 where we got all the other ones. Specifically for CSTRs, they're in 8.2.8.6. And there's this little subsection, 8.8.2, where they don't give a derivation, they just present that equation on the top as the multiple reaction system. So 8.8.2 is about half a page, and it says the energy balance for multiple reactions in a CSTR is this. And that's the extent of 8.8.2. But as we'll see when we derive the single one, it's not a huge leap to get to the multiple one. We can see the only difference between there is that sum term. So we'll see more of that. And regarding your homework for this one, this should be enough to cover 6.3 and 6.5, which is almost everything. 6.6 will ask you to work on the example that we're going to hopefully start today and finish up on Friday. I'm going to be showing you what those results look like. 6.6 is just take these numbers, put them into MATLAB, and show that the curves look the way that I show them on here. So 6.6 is not particularly difficult because we're going to solve the whole thing in here. It'll just be a matter of you showing that to yourself. Any questions before we get started on energy balances? I don't have exam grades. As soon as I do, I will get them to you. Probably Wednesday or Friday or Monday. Nada? Okay, let's roll. So if you dig back in your notes, back in lecture 13, we had introduced the following equation for an energy balance of a system at, I believe this was steady state. We had derived the amount of energy coming in minus the amount of shaft work, and then plus these two sum terms, where we had the amount of moles of stuff coming in times the enthalpy of that stuff coming in minus the sum of all the moles of things going out, Fi times the enthalpy of that stuff going out. So these sums, remember, were over the species, right? I is always our subscript for species, J is for reaction. So we found that energy balance. This is going to be our starting point for our CSTR balance. The CSTR energy balance doesn't look that much different from the energy balance, at least in terms of control volumes and whatnot. So remember, a CSTR has a little stirrer in there that has to be moving. And then there's a flow coming in and a flow coming out. In terms of those parameters that we got up on the energy balance there would be a molar flow rate coming in along with some enthalpy of each one of those species coming in, and some volumetric flow rate V naught. And then similarly, stuff coming out, Fi, Hi. Normally V coming out is the same as V coming in, because most of the time, again, with CSTRs, we deal with liquid CSTRs. It's unusual to have a vapor, but not impossible. And just like we have defined our control volumes previously, we're going to define our control volume as all of the fluid or all of the material inside our reactor. Unlike the control volumes we had to choose for the other two flow reactors where we had a plug flow and a packed bed, we're going to leave our control volume as the entire reactor volume. We don't have to take a differential slice here because we're going to make use of our well-stirred approximation. There are no concentration gradients inside there. The concentration inside the reactor is the same as the concentration coming out, so we don't have to worry about any variations inside there. That's from our well-stirred approximation. Like so many times, we're going to ignore the shaft work up here. About the only time that becomes important, again, is with polymer systems. If you didn't have a polymer, it's probably unlikely that your shaft work is significant, unless you're doing something like, running fluid through a turbine or something, then it's obviously significant. Turbines usually don't look like CSTRs, though. So from our stoichiometry, we know that we can get the outlet of anything, we'll use I for anything, is proportional to however much A was coming in, times that theta I and those stoichiometric coefficients times the conversion of XA. Same place we started before with all of our other flow reactors. If we put this into our energy balance, the energy balance actually doesn't change a lot. We still get Q dot, and we still have the sum of all the terms coming in. But now that term coming out looks a little bit nastier. I'm going to move it down a little bit. So now we have sum of FA naught, enthalpy of each species I, and then those annoying theta terms. They're not annoying, they're our friends, and XA. So all we do is put stoichiometry into our energy balance, we end up with something like that. So I'm going to give you 2 pieces of information, and then I'm going to give you about 5 or 8 minutes and see how far you can take this derivation, because I've derived the previous 3 for batch reactors, plug flow reactors, and packed bed reactors. This one has no differentials, so I'm going to give you 2 pieces of information and see how far you can take it. So those 2 pieces of information. The first part is from thermo. Remember, from thermo we can have the change in enthalpy with respect to temperature is equal to the heat capacity of any I, enthalpy of I. Which means if you integrate that, you can get HI minus HI naught has to be equal to C sub P I times T minus Ti naught. What is Ti naught in this case? Well, T is our normal T. This value of T here, that's the temperature of the reactor. That also happens to be the temperature of the outlet to our reactor. This temperature, Ti0, or not, however you want to call it, that's one that we haven't seen before because normally we don't care what the inlet temperature is. We do care about where we started, but we usually didn't call it inlet. That T is over here. So in an attempt to keep our nomenclature the same, that Ti naught shows up as part of our inlet. Most of the time, all your inlet fluids are going to be at the same temperature, but they don't have to be at the same temperature. So if you have different temperatures, for example, if you had a different stream coming in like this that had another temperature, that's fine. You just substitute whatever that inlet temperature is instead of Ti naught. Most of the time, for all the examples we're going to look at anyway, everything is coming in at the same temperature. But these equations work regardless of what that inlet temperature is. So that's one piece of information that we have. So you're going to have to substitute that into the energy balance. The other piece that we have is our material balance. So the material balance that we saw on Friday's class was that the volume of the reactor, capital V, is equal to the flow rate of A initially coming in times the conversion of A over minus RA. And that lets us write FA naught XA is equal to minus RAV. And this RAV term over here should look somewhat familiar because it's a term that shows up a lot in all of our reacting terms, right? That's roughly talking about the number of moles that are reacting. Molar rate times the volume gives you how fast they're reacting. So take these 2 assumptions, put them into the energy balance. I'm going to give you about 5 minutes to do some algebra and complete this equation, which is 0 is equal to Q dot minus stuff. There's going to be two terms there. One of them is going to include a sum of thetas, theta I times some stuff, maybe a factor out front, depending on how you write it, plus another something over here, we don't know what it is yet, that involves delta H. So take about 5 minutes here. Put those two equations into this energy balance, this one, and see if you can convince yourself that the output has to be a function that looks like this. I'm going to give you the answer when we're done, but better that you try it for a moment just so you see where all those terms are coming from. There shouldn't be any information that you need here beyond maybe remembering that delta H is defined as the sum of the stoichiometric coefficients times the enthalpies. But that was a definition, that's not really a derivation, we just said that's what it is. So take about 5 minutes, 4 minutes now because I've been wandering, and see what you can do. Does anybody have an expression for this term over here? What do you got?
Delta H times RAV.
Times RAV. Big V or little v?
Big V.
Big V, so that's your volume term?
Yes.
Okay. Anybody got anything different? There is another way that you could write that. Sorry?
I can tell you the other way to write it.
Sure, yeah, go for it. Delta H times what?
It's going to be delta H times FAO X. And put a negative in there.
Where'd the negative come from?
From the definitions you gave me from number 2.
Right, so if you look up here, either one of these, you'll see the energy balance for CSTRs written both ways. Sometimes you'll have it with the RA delta V. Sometimes you'll see it with the FA naught XA. You can do either one of those. It doesn't matter. If we have a single reaction, as we saw in a lot of previous examples with other reactors, we typically express it in terms of conversion. If you have multiple reactions, then we typically express it in terms of reaction rates. But you can use either one. If you have a single reaction, you're kind of stuck if you have more than one reaction using the rate terms. So either one of those would be okay. How about this term? So minus what? Somebody other than someone who's already answered. Anybody got a term there? First one's FA naught times sum of what? If you have one piece at a time. Theta I. H I. Well, we got to get rid of the H's. Yes, there is an H in there, but we got to get rid of those H's. Delta what? Well, we got to get rid of the delta too. So we want everything in terms of parameters that we can either look up or measure, and enthalpy is usually not one of them. Not directly. We can try, but we usually don't get very far. So this term is coming from, I'm going to write out the energy balance all the way and just talk about how the terms group to give us what we've got here and then give you the answer. I'll let you run through the algebraic steps. Most of you, it looks like you have the delta H term, and then I'll show you where the algebra goes to get the rest of them. So the version of the energy balance that we're dealing with is 0 is equal to Q plus a sum of Fi naught Hi naught minus the sum. So here I'm going to insert our stoichiometry minus Fa naught times the enthalpy of I times theta I plus the stoichiometric coefficient of I times XA. So a couple of terms are going to get lumped around here. Just to make sure the colors match, I'm going to flip back. So our enthalpy terms, in terms of reaction, are going to come from this term, our HIs times our XAs times our sum, right? Or sorry, times our stoichiometric coefficient. If we look at something like that, we end up with a sum of delta H, or sorry, that sum is sitting inside there. Delta H times an XA. That's roughly where that term is coming from because that sum shows up there. We have another one. Let's see, what color was I using for the other one? The purple terms, or pink terms, or whatever we have. We've got one term here that looks like Fi naught, Hi naught. But it's a sum. And then we've got another term over here that looks like a sum of Fa naught and theta I. Times what? There's another H floating around, right? So when we distribute that H, you're going to get one H that goes to the theta, basically the flow term, and one term that gets distributed that goes to the reaction term. Those aren't formal names. We don't call them reaction terms or flow terms. But the first one, where you look at Fa naught times Hi times theta A, that's talking about the flow of stuff going out. If you look at the Fa naught Hi times stoichiometric coefficient Xa, that's talking about things that are changing due to the reaction. So we can pull that term out, and we end up with something like sum of Fa naught Hi theta I. We can make these two look even more similar if instead of this Fi naught, we replace it with Fa. So now we have sum of Fa naught, Hi naught, theta I, minus the sum of Fa naught, Hi, and theta I. So now we've got a pretty similar looking set of terms in our sum that represents a difference between the inlet and the outlet enthalpies. The only difference now is how do we figure out what this Hi parameter here and this Hi parameter here are. If you want to take that next step, the next step is from thermo that we saw before, which is Hi minus Hi naught is equal to Cpi times T minus Ti naught. What does this assume about CPI? It has to be constant. If it's not constant, you can't really get an analytical form for this because you have to integrate that fourth order polynomial. Although you could, it would just have a bunch of polynomial terms sitting inside of it. So if you take those terms and substitute that into the energy balance, so this is the step where I'm going to leave it to you to substitute those terms in and show that you get the following answer. You end up with 0 is equal to Q dot minus Fa naught times the sum of your theta i's times your Cp i's times the difference in temperatures. Keep in mind that that Ti naught, we're going to use another T in a moment. That Ti naught is inlet temperature plus V times Ra delta H. That's one form of the energy balance. The other form is also fine. If you wanted to instead write this as minus Fa naught times Xa times delta H, that's also fine. Make sure you don't forget the minus sign out front. But either one of those are acceptable forms for the energy balance, so we might as well box this thing because we like it. So this expression is the energy balance for a CSTR for one reaction. So those are the elements that go there. Again, no differentials, which is nice. If it's adiabatic, our Q is going to go away, which will be the same as the Q that we've always seen before. Our Q term in general, if it's not adiabatic, Q is the same kind of Q that we saw before, which is minus capital U times A times T minus TA. TA is the same TA that we use in all the other reactors. This is your coolant temperature. Which we have assumed the expression for that coolant temperature is more complicated than what we've shown here. We have just assumed that that coolant temperature is constant. If you have a very large flow rate or you're using some sort of a condensate to do that, you can get away with that, but generally that Q term looks a little more complicated than what it is here, but to a first order approximation, that's not too bad. We can get away with that in most cases. 101B or a different section in your book would show you what the rest of that parameter looks like. Where is UA T minus TA coming from? We can jacket these reactors just like we could a batch reactor. So there's two ways we can get energy into or out of the system other than flowing material through it. So if you still have your sketch at the top, there's two ways that you can add or remove energy. One is to put a pipe in it and kind of swirl the pipe around inside. Right, and so now we could pump coolant in this way, it would heat up and coolant would come out the other way. The temperatures here are assumed to both be TA. They don't change. So that's the element that wasn't there on a batch reactor with a material balance. If you do have coolant, then you have something like that. The other way to do it is to wrap the heat exchanger. This is called a jacketed heat exchanger. In something like this, and then you have flow coming out here and flow coming in here. Again, both of which are at TA. The end result, as far as we're concerned, is always UA times T minus TA. But the behavior of both of those is a little bit different. Same as what we saw for batch reactors, though. Actually, those are the same as what we saw for packed bed and plug flow, except it's really hard to do this version. It's really hard to submerge a tube inside a plug flow reactor and expect that you're going to get decent heat transfer. It's rare that we put a tube inside there. It's really hard to do if it's a packed bed reactor. Yeah?
When you say jacketed reactor, like, what do you mean by that? Like, what is it, how is it covered, I guess? Or does it depend?
So imagine a bucket within a bucket. Let's say you wanted to cool something down. So you put ice in the outer bucket and you put your reactor bucket inside that ice. The ice will generally tend to cool whatever is on the inside. So in order to get flow to go through there, imagine somehow now you were able to pump that ice into that annulus around the two reactors and then pump it out in the other direction. And that's about all there is to most of these. Some of them are literally that simple, which is you dunk them in a bucket of something cold and circulate cold fluid around the surface of it. This one, the one that swirls, that one requires a little bit more effort because you can't just pick the reactor up and move it. Typically what that is like a copper tube that runs through the wall of the reactor and then gets turned around in coils inside the reactor. Actually, if we have enough time in week 10, I'll bring in a couple of the reactors we have. We have a jacketed reactor and a reactor that has a tube inside, which I think are usually called submerged heaters. So you can see what each one of those look like. It could be both, too. There's no reason you can't do both. I've never seen a reactor with both, but I haven't seen all the reactors in the world, so there could be both. All right, so any questions on our energy balance here? Doesn't look awful, right? No differentials, at least. This is, I think, the fourth time I'm going to show this equation, and we are almost to the point where this equation is going to become useful. Actually, you can derive this equation. So derive an expression for the concentration of, or sorry, the conversion of A for an adiabatic CSTR. There are two ways to do this derivation. One way is to rearrange that expression that I just gave you for the energy balance. So one way is to rearrange this, solve for x. The other way is to dig up one of the other 3 times we have written this equation. So that should tell you where we're going. So take a couple of minutes and see if you can derive this version of XA. All right, somebody who tried to find it in their notes. Next to wherever you found it in your notes, you would have gotten a plot that looks like this. What's that plot look like? What? Linear, right? There was a straight line. I would have drawn something that looks like this. And I probably would have mentioned that this is linear. And then I probably would have mentioned something like this is an EB for an adiabatic batch would have been the first one. We would have done a PFR first as the second one, followed by a packed bed reactor. Now we can add to that list the last kind of reactor, which is a CSTR. We end up with the same thing for another reactor. How do you derive it? There are probably a couple of different ways that you could derive it. If I just look at this equation that I've got back here, I'm going to get rid of Q because it's adiabatic. I'm going to use this version, the one with the XA in it, because I need to solve for an XA. Notice at that point the FA naughts are going to cancel, right? I can factor out an FA naught and put it over on the other side to get rid of it. And all I'm left with is 2 terms. I have a sum of theta I CPI T minus Ti naught and an XA over delta H. If I rearrange that equation, which is the entire length of this derivation, so it's about 3 steps, I'll get sum theta I CPI times T minus Ti naught divided by minus delta H. So this, again, represents a linear relationship between the conversion that I have and the temperature of the reactor. Generally, if I increase the temperature of the reactor, the conversion will go up or down. Oh, it depends.
By graph, of course, if it's endothermic, then it's going to go the opposite direction.
Yes. So it does depend on the sign of delta H to tell you whether or not conversion will go up or down with a change in temperature. But nevertheless, the relationship is linear. And it's that linearity that's going to help us. I think we'll end up getting to it on Wednesday of next week. I don't remember looking at the syllabus at exactly where we get to it. So again, as for now, this is as far as we're going to take the adiabatic relationship. If you happen to have an adiabatic problem on a homework or an exam, that's the same expression that we're going to use that we've seen before. Some of those subscripts on the T might be, this T I think looks a little bit different than what we saw before, but conceptually it represents something similar, which is the enthalpy change needed to heat something up. Last example, oh actually I need to make 2 quick modifications. If you have multiple reactions, there's only 2 changes that we have to make. They're the same 2 changes that we've made for almost every other reactor that we've got. In fact, for every other reactor that we've got. Instead of a single R, we now have to figure out the net rate for each species. So that R ends up looking like the sum of Rij for j equals 1 to n, or sorry, j equals 1 to q. Q is what we use for reactions. And then the only term that changes in your energy balance, by the way, the reason your book doesn't give, or at least the reason I assume that your book doesn't give a derivation for this, is because they're a little sloppy with their definition of I. I is whatever that special species is for each reaction. it's not really that you're summing it up over all species. You're summing it up over all reactions, and for each reaction, you have to choose a special species I for each one. So, for example, when I wrote the derivation for this, it's easier for me to derive this if I write down 4 reactions and just write down these expressions for each one, and then extrapolate to this sum term. But it's the same Rij delta Hij term, summed up for all j equals 1 to q reactions. So you're kind of stuck if you have multiple reactions. You have to use that Rij delta Hij term. These two things combined, how's the rest of that song go? Something about let our powers combine. Jenna would know. Wait, what? Somebody
I
know?
was saying you can't rhyme combine with combine. That's a cop out.
It does. It is kind of a cop-out, right? Nobody remembers the Captain Planet theme? Yeah. If you increase the level of your voice, I will give you a +1 bonus point on your homework.
Captain Planet, he's a hero.
Yeah. Hey, good enough. No, seriously, see me after class. I'll give you a bonus point for that. I feel so thankful I'm not old. Anyway, if you combine these things, you typically are in a situation where you have to solve multiple nonlinear equations, and you typically have to do it simultaneously. We've actually already solved nonlinear equations, multiple nonlinear equations simultaneously. The other place that this comes up a lot was on one of your homeworks. You would have encountered the Gibbs reactor. No groans for the Gibbs reactor? No? Everybody loves the Gibbs reactor? It's a pretty good reactor. We had to solve multiple nonlinear equations there as well. But for any CSTR that's got more than one reaction going on inside of it, you typically have to solve both the material balances, one for each species, as well as the energy balance simultaneously, which is the part that gets a little bit different from what we saw with our other 2 flow reactors in the batch reactor. There, we didn't really have to do anything different. We just added more terms to ODE 45, and it magically handled them all just fine. If you need to solve multiple multiple nonlinear equations simultaneously, there are quite a few tools that can do this. I don't have a preferred tool that I'm going to ask you to use. I'm never going to ask you to write code to do something like this on an exam. So I don't care how you come up with this solution. The tools that I am aware of, which I had a list around here somewhere. I seem to have misplaced my list, so let's just start coming up with ones. The tools, shocking. The tools in MATLAB are functions such as F0. F0 can do it. There's another one called fsolve that can do it. Those are the only 2 I know of in MATLAB that'll solve these kinds of systems. Fsolve will do it explicitly, right? You can just provide it the equations that you need, it will solve them all together. F0 is a little bit more roundabout. You kind of have to keep calling F0 a few times. So it's up to you. If you like either GoalSeek or the spreadsheet, or the Google Sheets, or what's the open source one? LibreOffice, LibreSheets, whatever. LibreCalc, I think is what it's called. Those should all have a function in them called GoalSeek. If you're clever, you can make GoalSeek do it. If you have Excel, Excel has a slightly more powerful version of GoalSeek called Solver. There's also the actually I think it's just called, does anybody have an TI-89 with them? I think it's just called Solve. I'm going to put it in quotes because I'm not sure exactly what that is. But your calculator has a way to solve nonlinear equations. There's also Wolfram alpha. Actually, alpha could have trouble with it. You might have to go all the way back to Mathematica. Does anybody use anything else? I mean, certainly any of the programming languages like Python or Octave or C or anything like that, it will, sooner or later, you'll be able to find something like that. But you can take your pick as to which one of these you need. On the homework, I don't think I gave you anything that requires one of these except as a bonus. So one of the problems makes you solve one of these or asks you to solve them, but you don't have to solve them unless you want, like, I think it's 2 points on that homework problem. Yeah?
Does symbolic math work on these as well?
Yeah, symbolic math would be able to take care of this too. I think in symbolic math that function is, it's either solve or fsolve again. I can't remember which one. But yeah, symbolic math can take care of this. So I don't mind how you want to solve these, and the only time you need to solve them is if you want that bonus point on the homework. Unless you're dealing with a real system and your boss comes to you and says, solve this problem. Now maybe you need to solve the problem for a reason other than bonus points. So I think we've got enough time to introduce the example that we're going to get to cover in more detail on Friday's lecture. So I'm just going to describe the system. We're going to come back to this on Friday. So at the beginning of Friday's lecture, I will probably have this drawn up here again, but it's going to be the same thing. So we're going to pick really easy numbers so that we don't have to worry about unit conversions or anything like that. Here is our CSTR. Of course it has a mixer in it, and that mixer is active. And we've just got a single flow coming in and a single flow coming out. We also have a heat exchanger, which actually, since we're working with the heat exchangers now, maybe I'll try to bring one of those in on Friday so that you can see what a jacketed heat exchanger looks like. And that's about it. To make this about as simple as possible, we're going to say that the flow coming in of FA naught is 1 mole per second. We're also going to say that there is no B coming in, so FB naught is 0. It's going to come in at a volumetric flow rate of 1 liter per second. We're just going to pick a temperature coming in T naught of 325 Kelvin. The volume of our reactor, V, is going to be 1 liter. Try to keep that, again, as simple as possible. And our heat exchanger, U, is going to be 1,000 watts per meter squared Kelvin. Our area, what do you think our area is going to be? Haha, nobody could have guessed that I would say 0.3 meters per second, or sorry, meters squared. And the coolant temperature, which is constant, is another 325. So our question for this is going to be determine X, the conversion of A. What kind of reaction is going on inside here? We have A goes to B. It's an irreversible reaction, right? So we really are trying to keep this as simple as possible, except for that 0.3. The delta H, in terms of A reacting, is minus 100 kilojoules per mole A. This is also a constant, so we don't have to worry about that. There will be one variation, which is our rate constant K is 0.0, oh, you can't have multiple decimals, 0.1 inverse seconds. This is at 300 K, so we're going to let this one vary a little bit. And our activation energy is 50 kilojoules per mole A. Or sorry, just kilojoules per mole. So there's not a lot of, actually, if you have a little bit more information, we need those, or a little bit more space. I'm going to shift these up because we need heat capacities too. The heat capacity of A is equal to the heat capacity of B, and both of these are 30 joules per mole Kelvin. And they're both constant. So there's not, it looks like a big smattering of information, right? There's a bunch of information there, but all of the values that we need to solve the energy balance are there. We'll need one other piece to adjust K. What do we use to adjust K? The Arrhenius expression, right? We've got an EA here, so we can adjust this K to any T that we need. But otherwise, there's not really that much interesting going on. Other than when we are all done, we're going to find the following, which is that X, where did I write these numbers down? There it is. X is only 0.5%. X is also 38.5%. And X is also 96.8%. So this concept is what we're going to talk about on Friday. How is it possible that a seemingly normal set of equations, there's nothing fancy about this, it happens all the time, can produce multiple values of X, all of which are acceptable values of X. Your reactor could really operate with 0.5%, 38.5%, or almost 97% conversion. So we'll talk about how we figure that out and how we choose which one of those we operate at. Thank you all very much. I will see you on Friday.